is we're going to explore the spring skies. So essentially the skies that we would see if it were clear tonight. And if it magically clears up, we'll be able to point out some of the constellations and some of the objects. But if it doesn't clear up, this is the next best thing, I think. So here we can see a flattened, kind of a Mercator style map, a flattened map of the entire celestial sphere. A little bit earlier you were looking at the glowing blue celestial sphere over here. What we've done here is we've taken that celestial sphere, smushed it, and then rolled it out into this map. You'll see a purple line going across the center there. That purple line going through the center is the celestial equator. So just like the equator around the Earth, which separates the Earth into a northern hemisphere and a southern hemisphere, the celestial equator separates the northern and southern hemispheres of the celestial sphere around us. You'll also see that yellow line going through that kind of looks like this. We would call that a sinusoidal curve there. That is called the ecliptic. And the ecliptic, just like the equator, is a loop around the celestial sphere. Now the celestial equator, if we were to take Earth's equator off and then expand it against the celestial sphere, that's where the celestial equator would be. It's literally right above Earth's equator. The ecliptic is on its side. Now really, it's not on its side. The Earth has a tilt, a 23.5 degree tilt as it's orbiting around the sun. So the ecliptic is essentially the plane of the solar system. So it's right there where you will find the sun, the moon, the planets. They'll be somewhere on that line. And that line extends from the east in the south and then goes down in the west. So you'll only see the planets along that path. You'll never see Jupiter over here or Saturn over here or the moon down there. And if you do, it's like the end of the world. Something really bad has happened. It'll be somewhere on that line. Now, why does it have that curve? Well, you see, when we flatten that map, our lines, our circles here, can only do certain things. The equator opens up in a straight line, but only one of them can be a straight line. Look at what happens when we tilt it and then we flatten our map. It creates that kind of sinusoidal curve, and that's what we're seeing there. So where is the sun right now? The sun right now is about, I'm going to have to come over here. There it is. Should be right about there. The sun is in a position, you'll notice right up here where the ecliptic is at its highest point above the celestial equator. That's the summer solstice. That's when the sun is at its highest point in the sky. And if that's the summer solstice, you can probably guess what that is, can't you? The winter solstice. That's why we have winter. The sun still travels across the ecliptic, but the ecliptic isn't very high at that time. So we have less hours of sunlight, and we have less direct rays of sunlight. 1 + 1 = winter time is essentially what's happening. Whereas here, it's very, very hot. We have more sunlight, more direct sunlight, more hours of sunlight, and we have summer. And then here, if these are the equinoxes, or excuse me, I kind of just gave it away. If these are our solstices, right here and right here, when the sun is crossing, the ecliptic is crossing the celestial equator, we have our equinoxes. So right now it's about here, in between April and May. Right about there, about June 21st, is going to be the summer solstice. June, July, August, September. So there's the September or the fall equinox. September, October, November, December. Around December 21st is the winter solstice. December, January, February, then back to March again. And we just had an equinox, the March equinox, around March 21st. As the Earth orbits around the sun, we are privy to different parts of the celestial sphere. In the north, there are constellations that kind of stick there the whole time, but in the south, it's constantly changing for us. During the summertime, you are looking towards the center of our own galaxy. During the wintertime, you're looking out the spiral arms of our galaxy. And this is one of the reasons why during the wintertime, the stars look so much brighter. It's not just the temperature, but it's also the fact that you have a backdrop of darkness. Whereas in the summertime, you have a backdrop of billions and billions of stars. So to you, it seems like there's the same number of stars, but they just don't look as bright because the background just doesn't get quite as dark in the summertime.
That's crazy.
Right now, we are looking kind of sideways out, and we can see a lot of galaxies. Yeah.
I have a neighbor that I sat out in the middle of the street to watch the moon here a while back. And he was saying when he went to Valentine, and I'll bet it was like this, he said, he got out there and he looks up and he says, oh, it's all cloudy.
Right. And it wasn't clouds.
What? And it wasn't cloudy. And he said it took him a while to realize that he was looking at a trillion stars.
It was that Milky
and
Way.
He was just absolutely awed by that.
I've seen it a few times. That Milky Way, those stars are so bright that you can hold out your hand. This is at the Nebraska Star Party, not around here. You can hold out your hand and the starlight from the Milky Way will cast a shadow of your hand onto the ground. That is how incredibly bright those stars are. That's how beautifully dark the rest of the sky is. It is incredible. Just when it just starts to get dark out there, you can already see as many stars as you've ever seen out here. And then all of a sudden, it gets darker and it kind of hits you because it's so incredibly dark. But here's the neat part. Your eyes are pretty amazing machines themselves, and they adjust to that darkness. And after about an hour, your eyes dark adapt so well, you don't need a flashlight. You can walk around under the starlight. Absolutely beautiful. This is the Milky Way here, and we are actually looking towards the center of the Milky Way. That's why it's flatter here, and then we have this larger area here. This is the spring night sky, and when I give any of these programs, whether it's the spring program or the summer program or the winter program, what I do is I choose, I'm essentially doing 3 months of time. And so what I have to do is choose a night sky that represents different times during those 3 months. So this would be 1 in the morning, pretty late on March 15th. This would be 11 p.m. tonight, about April 15th. And then it would be about 9 p.m. next month, so a little bit earlier. Then after that, I will start doing the summer program. I'm going to go ahead and rotate this entire thing. So north is on the bottom, then let's zoom in. And when we zoom in, one star will jump out more than any of the others, right there in the middle, a very famous star named Polaris that I know each of you know. Polaris goes by a much more popular name, doesn't it? That's right, the North Star. Polaris is also known as the North Star. Now, something that will surprise you, might surprise you, is that the North Star is not only not the brightest star in the sky, it's not even close. It's the 49th brightest star in the sky. The North Star is famous because of its position in the sky and what it's been used for hundreds of years. The North Star is very, very close, not exactly, but very close to the North Celestial Pole. You'll remember our Earth is tilted on its axis. And if you were to extend this axis into space, and I have a neat little demonstration here where I took a laser pointer and stuck it right through a globe here, and I can shoot that laser pointer. It points at a position in the sky called the North Celestial Pole. And as the Earth turns, that point is still there. I can kind of do this and turn that on. The point is still there, but the Earth is rotating. So if you were on the Earth from your point of view, it makes it look like the stars are moving and they make circles around the North Celestial Pole. And because the North Star is so close to the North Celestial Pole, it circles a little tiny, tiny thing. It essentially looks like it's stuck right there in the sky. So the North Star is always in the north. However, it can get higher and lower depending on where you are. And here's the fun thing. The altitude of the North Star tells you what your latitude is. They're equal. Right now, our latitude is 40.95 degrees north latitude. If you were to go outside and you get a protractor and you measure how high the North Star is, it'd be about 41 degrees above the horizon. So if you ever find yourself maybe on a ship in the middle of nowhere, and you don't know where you are, just look for the North Star, measure how high it is, pull the protractor out of your pocket. Actually, your phone does it, right? You can get the level on, pull out your phone and put it on the level, and then measure how high the North Star is. That's what your latitude is. Now, longitude is a whole different thing. It's a little bit more difficult. And if you have a phone, call somebody.
Is that part of what an astrolabe is for?
Absolutely.
Okay.
That's part of exactly what it does. Now, the North Star can be higher or lower depending on your location. So if you went to North Dakota, it'd be a little higher in the sky. Canada, higher. Alaska, higher. And if you were at the North Pole of the Earth, where would the North Star be? That's right. It'd be at your zenith, straight above your head. Now, think about what that means. If all the stars are making circles around the North Star, that means that if we chose a star right on the horizon, throughout the night, 24-hour day, and throughout the year, it would do this. It would never set. No stars rise and no stars set. If you're at the North Pole, you're stuck with the same constellations year-round. On the equator, it's quite the opposite. On the equator, the North Star, as you travel towards the equator, the North Star is going to go lower and lower and lower and lower, and then finally, you can't see the North Star anymore. All the stars come straight up in the east, over your head, and go straight down in the west. There are no what are called circumpolar stars. They're all rise and set stars. So these stars here for us, these are called circumpolar stars. They're always up. The Big Dipper is always up. The North Star is always up. Cassiopeia down here is always up.
I never thought of that.
It might be upside down, it might be right side up, it might be over here, it might be over here, but it's always up during the day and during the night. These are all our circumpolar stars and circumpolar constellations. But how do we find the North Star in the sky if it's not nearly as bright as I think people think it is? Well, as you can see, it's in the end of the handle of the Little Dipper, also known as Ursa Minor. We'll talk about that in a moment. But the easiest way to find the Little Dipper and the easiest way to find the North Star is to first find the Big Dipper, because the Big Dipper is easy. Big Dipper is big and it is very bright, and during this time of the year it's upside down. So again, it depends on the time of year you're going out and the orientation that it's going to be in. But find the Big Dipper using the two stars in the end of the cup of the Big Dipper. Those are our pointer stars, and they will point right to the North Star. It's that easy. And then the North Star is in the end of the handle of the Little Dipper. These stars here, here, and these two stars here are pretty difficult to see in the actual night sky. Out here at Branched Oak Observatory, out at Nebraska Star Party, easy to see. But out here, these four stars right in here are relatively faint. The Big Dipper and Little Dipper are in constellations. They are not constellations. Not all those patterns in the sky are called constellations. There are 88 constellations, and that's it. 88 constellations. These other ones are called asterisms. The Big Dipper is in a constellation named Ursa Major, the Big Bear, or the Greater Bear. The handle, and the bear's upside down too. The handle is the tail of the bear. There's his back leg. There's his tummy. We'll tickle him a little bit there. There's his chest, his front leg, the bottom of his neck, tip of his nose, and his back all the way up like so. Now the bear is about twice the size of the Dipper. And I'll tell you, us astronomers, this isn't what we do. We don't go on out and look for constellations, but they are important because they're a map. They are a sky map, or I like to call it a treasure map, to find these amazing treasures. For example, I know right here above the head of the bear, we have two beautiful galaxies. One is named M81, the other one is named M82, or Bode's Galaxy and the Cigar Galaxy. And what I really like about these two galaxies is that we can get two galaxies in the same field of view. One is face on, the other one is edge on. So it's kind of nice to see the two galaxies in those two orientations. These galaxies are 11 million light years away. 11 million light years away. That's very, very big. And the distance between them is about 150,000 light years. That's about the size of our own galaxy. Our galaxy is probably 100 to 150,000 light years. So our own galaxy, the Milky Way, would fit very nicely in between those two galaxies. Now we've mentioned light years a few times here. A light year, even though it has the word year in it, is not a measurement of time, it's a measurement of distance. Light travels really fast. I've got my neat laser pointer here that I've been using to turn things, and if I turn on my laser pointer there, and if I hit my laser pointer and at the same time, oops, accidentally drop it onto the ground, gravity would take it, and it would take about a half of a second to hit the ground. In a half of a second, that laser, if it could curve, it could go around the earth 3.5 times. That's how fast light is. 2.9 times, it's actually 2.99 times 10 to the 8th power meters per second, or it's 186,000 miles every second. It's very, very fast. 6 trillion miles. But we need to use this type of measurement when we talk about things that are so far away. The nearest star to us after the sun is a star named Proxima Centauri. It's about 4.25 light years away. And this brings up something that in astronomy we call look-back time. Because when we look at this object that's 4.25 light years away, we're looking at what it looked like 4.25 years ago. And this galaxy here, the Andromeda Galaxy, is 2.5 million light years away. When you look at it, doesn't matter if it's with a telescope or with a pair of binoculars, you're looking at what it looked like 2.5 million years ago. So as astronomers, we're time travelers, sort of. And our telescopes are time machines. So the further back in you're looking in space, the further back in time you're looking. So it is really exciting. Let's take a look at another galaxy. Here's another galaxy right in the tail of the Big Bear. Its name is M51. This galaxy is about 31 million light years away from us. And that galaxy there, you can see it has an arm that's grabbing another galaxy, saying, come on over, come on over. And that's how galaxies change their shape, is through gravitational interaction and even collisions with other galaxies. Speaking of collisions, there's a galaxy, the Andromeda Galaxy that we talked about earlier. It's on its way towards us. In about 5 billion years, our galaxies will collide. We don't have anything to worry about. It's a long ways off. The second star in from the end of the handle of the Big Dipper, it looks like one star, but if you look at it very carefully, if you've got good eyes, you get your glasses on, you might be able to see there appear to be 2 stars, but that's a fib too. Because if we take out a telescope, we find out that Mizar here, the brighter of the two, is made up of 2 stars. And each of those 2 stars are 2 stars. And then Alcor up here is a double star as well. So instead of 1, instead of 2, there are 6 stars there, all dancing around a common center of mass and kind of doing a cosmic hoedown in space. Let's go ahead and move the sky. That dotted line, there's our ecliptic. Now you might notice something. That ecliptic is passing through some very particular constellations. You see, ancient astronomers, they weren't dumb. They knew their stuff. They knew the sky a lot better than we did in many ways. And they could see that the planets would travel through, and the sun and the moon would travel through certain constellations. And they figured, you know what? Those constellations must be special. They must be different. And they named those the constellations of the zodiac. So we are astronomers here. We're not astrologers out here, but the constellations of the zodiac do exist. As a matter of fact, at one time there were 13 constellations of the zodiac, but when we moved over to the Gregorian calendar with 12 months, they had to kick one of the constellations of the zodiac out. You want to know its name?
What?
It was Ophiuchus the snake handler. Yeah. So who knows, if we hadn't have gone over to the 12-month calendar, maybe one of you would have been born as a Ophiuchian as opposed to a Gemini or a Leo. So we can see there's Gemini, there's Cancer. I know it's not drawn out, but I'll show you Cancer in a moment. And there's Leo the lion up there. Here we can see the Gemini twins. And the Gemini twins are on their way down. If we went out right now and it was clear, they'd be a little higher in the sky, because this is at 11 p.m. But at 11, they'll be a little lower in the sky. They look like 2 stick figures standing right next to each other. And right now, the planet Mars is inside of the Gemini twins. So it's right next to them, but not for long. I've actually seen Mars slowly moving along the ecliptic, and it's very bright, and you can just barely see a little bit of color to it. In a telescope, you can see that